Section 12.1 is the introduction to geometric solids. The rest of the chapter is going to look at surface area and volume of these geometric solids, but this will at least provide us the introduction to these types of objects we'll be looking at. So, first off, we're going to look at our family of polyhedrons. Now, these are going to be solids bounded by polygons, and a basic example we have of that is a rectangular prism, which we have right here. If we look at the rectangular prism, you would think of it like a box. It's made up of all rectangles. Now I realize that if I were to draw this, it makes it look like a parallelogram, actually here and up top. But that's again because we're having depth to it. We want to show 3 dimensions. So we want to think of this as all being rectangles bounded together. We have a few other types we could just draw. We're going to define them in a minute, but we could also have a box that maybe had a triangle as a base. I could draw a triangle for the top, a triangle for the bottom, and then connect them to give me what we'd call a triangular prism. We could also have something that we're going to call a pyramid. And this is one where we draw the base. This is a rectangle again. But this time, we're not going to have a top and a bottom. We're going to have that bottom base and a point at the top. Just like the pyramid you would think of. Now, all of these are made of polygons. Rectangles, rectangles and triangles, rectangles and triangles. What's not going to be a polygon is a circle. So as long as there's no circles here, we're going to have their own set of solids like that. We're going to be looking at polyhedrons. So of those polyhedrons, we have some parts. We have the face, and that's the polygons that enclose the region of the space. Those are the polygons, those are the walls, those are the sides, those are the pieces that make the object. We have the edge, which is the segment formed by the intersection of the two faces. Well, we could also think of that as the lines you draw. As I drew these objects, I was drawing the edges. I don't actually draw the face because it's the edge that kind of defines what that face is. If I was to draw a rectangle, I'm drawing the lines, the edges to the outside. Inside of it is the rectangle. So the lines you draw are the edge. The vertex is a point where 3 or more edges meet. We could think of that as the corner. In this rectangular prism, I have these edges where the 3 lines, or these corner, try again, these vertices, or vertex, where 3 lines meet. It's kind of like the corner of the box. If this was a room we were standing in, that corner would be down here, where those 3 lines meet. The walls meet the floor. That'd be a vertex. Now, let's look at our types of solids. We've already mentioned polyhedrons, which is, or the polyhedra, if we don't think of it as a singular. That's a prism and a pyramid. And these are all made with polygons. Now, I mentioned we could have it not made with polygons and made with circles. And that's where we have our not polyhedra. Made with polygons, not made with polygons, made with circles. Now, they may have parts that happen to be still polygons. We're going to see that later with a cylinder. But the fact there's a circle in it shows it's not going to be a polyhedron. Now, we're not going to have faces, edges, and vertices over here for the non-polyhedrons. That's only going to be the polyhedrons, the prism, and the pyramid. And that's something we're going to see a little bit later on as well. Now, for a cylinder, cone, and sphere. Particularly the cylinder and the cone. These are kind of the circle version of the polyhedrons. If I look at a prism and think of the circular version of it, so instead of a rectangle, I'd have a circle, that would be a cylinder. If I looked at a pyramid and instead of this rectangle on the base, on this bottom piece, I had a circle instead, it'd be a cone. And then a sphere, we could just think of as a ball. That's a 3-dimensional round object. Has that circle cutting through it almost like an equator. Now, let's go back to our polyhedrons a little bit. We need a better way to define them because, well, honestly, cylinder, cone, and sphere, depending what size they are, how wide, how tall they are, they're generally going to look the same like a cylinder, cone, and sphere. But we're going to find there's some variation between a prism and a pyramid. So we have to be careful with how we classify them. So to classify a solid, and we're going to be particular here and say a polyhedron. So to name a prism or a pyramid, you use the shape of the base. So here I have a pentagonal prism. This is where I have a pentagon on the top and the bottom of the solid. The walls going around it, if this was a room, would all be rectangles, and that'll always be the case for a prism, regardless the number of sides it has, they'll still have rectangles going around for the walls. But it's that top and bottom, those bases. In a prism, these bases are also parallel to each other, and they have to be congruent to each other. So they're the floor and the ceiling, they're going to be congruent and parallel. We want to keep that in mind, so just in case the shape was rotated, I wouldn't mix it up. I wouldn't think that this is a base because there's no other parallel side or wall or face that's parallel to it. The one opposite doesn't work. Now, with that in mind, if we had that box, that rectangular prism before, we could theoretically rotate it around and maybe get a few different ways to look at it. But for this one, our bases are pentagons, so it's going to be a pentagonal prism. We look over here, we have a base that's a triangle. So that's going to give us a triangular pyramid. Now a pyramid is going to have the flat base on the bottom, and it's going to have the point that each corner or each vertex on that base goes to. This does not have two bases. It just has one, goes to a point, but since it's a triangle on the bottom, we call it a triangular pyramid. So if we go through a few other examples and just get used to identifying them, because calling it just a prism or a pyramid, we're going to use that for when we classify or when we solve for surface area and volume, but in terms of classifying, we have to make sure we're identifying it correctly. So, look at my first one here, and if I shade in the bases, I see that they're triangles. So this would be a triangular prism. Next one can be a little deceptive on how you see it, but if I look at those two rectangles that I have, it almost looks like the front and the back, those are not congruent, so we can't call those the bases. Our bases are actually these objects, which hopefully you recognize as trapezoids, and we call it a trapezoidal prism. Okay, next one we look at, we have one base. It goes up to a point, so it's going to be a pyramid. And if we look, our base is a hexagon. So that'd be a hexagonal pyramid. Okay, lastly, we look at our base on this one. Looks like a rectangle. So we call it a rectangular pyramid. Now, to go a step further, if I had that all these sides were marked, I would maybe have that it could be a square, could be a rhombus, and we could get more specific. Generally, you will see the triangle, rectangle, hexagon as your most common bases, but keep in mind you could have a trapezoid, you could have parallelograms, you could have pentagons, octagons, really anything that we found area with in chapter 11 could be fair game for a base to use. And we're going to see that when surface area and volume comes up in later sections. We use those base formulas to help us find surface area and volume. Now, also in this section, we're going to have an introduction looking at Euler's theorem. And this is a relationship between the number of faces, vertices, and edges within a polyhedron. Now, this relationship always exists, and that's the number of faces plus the number of vertices is equal to the number of edges plus 2. So we can look at our object, we can count, and it should come out to give us a true statement where both are equal to each other. So for example, I have this rectangular prism up here. Now if we think for a second, what if all those sides were in fact the same? If all the sides were the same length here, we would actually call this a cube. So a cube would just be a rectangular prism where all the faces were the congruent squares. But that's what we're looking at. They say we have 6 faces. Faces are those sides, those polygons that we have. There's the 4 going around, the top and the bottom, so that gives us 6. Vertices, 8. That's the corners, 1, 2, 3, 4, 5, 6, 7, 8. Okay? And edges are the lines you draw. If we look at the top, we have 4 there. The bottom, we have 4 there, and we have 4 connecting. That gives us 12. So 6 plus 8 equals 12 plus 2, 14 equals 14. That is a true statement. We know the relationship is true. So if we look at examples of our own. First, I'm looking at a triangular prism. If I count the number of faces, I have the top and the bottom, those bases, those count as faces. So that's 2, and then I have 3 walls going around, gives me a total of 5 faces. Vertices is the corners, 1, 2, 3 on top, 1, 2, 3 on bottom, gives me 6. Edges is the number of lines. If I look at the top triangle, I have 3 lines there. Bottom triangle, I have 3 lines, and I have 3 lines connecting them. That gives me 9. 5 plus 6 equals 9 plus 2. It's like 11 equals 11, so we know we're good. Next, I have a rectangular pyramid. If I look at the number of faces, well, I have my base, that's a rectangle, and then I have the 4 sides of the pyramid going up to the point, so that would give me 5 total. Vertices is corners, 1, 2, 3, 4, 5. Edges, number of lines, I have 4 that give me the rectangle, and then 4 that go to the point, gives me 8. 5 plus 5 equals 8 plus 2. That one checks out. Now, what you may see typically for these types of problems, they may give you an object like either of those and ask you for faces, vertices, and edges, how many you have of each. And in that case, you would just go through what we do, and you would use Euler's theorem to check to make sure it matches. Another one you may have is maybe they give you faces and vertices and you need to find edges. Well, if that's the case, you'd set it up and you'd solve for your unknown value, so you could use it in that respect also. It should be equal, though, when you check with Euler's theorem. If it is not equal, you need to go back and check your answer. One thing I would check is be sure you did not switch these 2 values. It's very common to switch vertices and edges. If that's not the case, just go back and make sure you've counted them. But as we go through them and get practice from them, you'll get good at counting them, and that shouldn't be an issue. So let's look at another example. Now, we already did a rectangular pyramid. Let's look at this shape. First off, we have to look and make sure we can classify it correctly. We look at that one, we see it has bases. It does not go to a point, so that means it is a prism. But we have to make sure we correctly identify what the base is. Now, I have this rectangle here, and it looks like it matches to a rectangle there. I'm not going to make that the base, because if that was the case, this odd shape over here would have to be a wall, and those walls always need to be rectangles. Well, the fact this shape is not a rectangle means we could look at it. Let's see if you can see it here. That's shaded in lightly, I guess. We see this shape could be a base, and this shape matches it on the other side, also could be a base, so that means it's going to be a hexagonal prism. So that classified it. Now, maybe if you wanted to redraw that, maybe look at it a different perspective. We haven't talked about much drawing these, but it's always good to get practice. You're going to get plenty of practice as the chapter goes on. But I could draw my base. I could draw up the walls. The front wall and the back wall, if I was looking at it. And then I just draw on the sides. Now, maybe that's not the way you would draw it. Maybe you'd go through a different step. But in the end, you need to be able to look at it, and this needs to clearly show that the hexagon are the bases, and it forms a prism. So keep practicing as you go through these. You're going to need to be able to draw them towards the end so you can clearly identify and represent your work. Now, the number of faces. I have 2 bases, top and bottom, and I have 6 walls going around. Gives me 8. The number of vertices. That's the number of corners. I have 6 on top, 6 on bottom. Gives me 12. The number of edges, that's the number of sides, or the number of lines drawn. I have 6 to make the hexagon on top, 6 to make the hexagon on bottom, and then 6 to connect. Gives me 18. Well, I have my answers. I might as well check with Euler's theorem. Let's see, 8 plus 12 equals 18 plus 2. It looks like 20 equals 20, so our values are good. And again, if you get an answer that doesn't match here, always look first, did you switch vertices and edges? It's a very common error. And then go back and recount faces, or the number of polygons you have, including the bases. Vertices are the number of corners, or where the lines meet, the intersections, and edges are the lines you've drawn.